we're diving deeper into reliability and validity in clinical assessments. So a reminder, and some of this will be a review from last week, but it's still important to go over it again. So as a reminder, reliability in the world of psychology is the consistency of the findings or results of a study or a test. So if findings or results remain the same or similar over multiple attempts, we can consider the test or measure method reliable. Validity is questioning, is the instrument measuring what it claims to measure? So it's the extent to which a test does measure what it claims to measure, and it's really vital for a test to be valid in order for the results to be accurately applied and interpreted. While validity examines how well a test measures what it is intended to measure, reliability refers to how consistent those results are. So a reliable test produces similar scores across conditions and situations, including different evaluators and testing environments. And ultimately, there are 4 different ways to assess reliability. There's the internal consistency, inter-rater reliability, parallel or alternate forms reliability, and test-retest. And we'll get into each of those. First, we want to know, how do we account for an individual who doesn't get exactly the same score every time he or she takes the test? So this is really looking at what are some factors that affect the reliability of the test or measurement. And the first one is simply changes in the test taker's ability, motivation, or attitude. So if the measure itself is a little unclear or open to the test giver's interpretation, how the test is actually administered can be impacted. Even if the test has really clear, concrete instructions, humans are variable beings. So how a test giver facilitates a test one day may be different on the next day. And similarly, how a test taker completes the test on one day may be different on the next day. It's possible that they feel more rushed or less motivated when completing the test the next time. And that's certainly going to then impact their scores. It could certainly account for a lower score if this is a knowledge-based assessment. It could also account for lower ratings on mood or energy level, depending on how the person's doing. Changes in environment like comfort level and noise also can affect reliability. Certainly, we can all think of a time when the environment impacted our ability to concentrate and recall information. The environment can have a significant impact on test scores. This is particularly true for tests that are assessing a person's knowledge base. If you administer an anxiety screening to a client in a busy, crowded room and then give them the same screening 2 hours later in a quiet office, chances are the client's going to have reported a higher anxiety score while in the louder environment. Characteristics of the measure itself will also affect reliability. So if the measure itself is changeable or has some sort of fluidity to it, you are likely to get different results each time, even if the results are really close. Examiner characteristics is another one. So if test giver A on day 1 has a very thick accent, for example, and it's difficult for the test taker to understand it, and then test giver B on day 2 does not have that accent, we can't regard those 2 test scores as particularly reliable results. It's very possible that the person taking the test scores better on the version that was administered when it was easier for them to understand what was being asked or told of them. Finally, unknown error accounts for the unknowns, right? Basically, other factors that impacted the test that we weren't able to identify specifically. It may be ultimately examiner characteristics or characteristics of the measure itself. It may be a data collection error or some other error. But the point is that it's unknown. So this is another piece that we do have to factor. The reliability coefficient is a way of confirming how accurate a test or measure is by giving it to the same person more than once and then determining if there's a correlation. So it expresses the degree of consistency in the measurement of test scores. And you'll see on the screen here that it's denoted by the letter R with those 2 identical subscripts. Remember that the correlation is the strength of the relationship and similarity between the 2 scores. The correlation coefficient which is often referred to as Pearson's correlation or product moment correlation efficient. This is a statistic that is used to estimate the degree of the linear relationship between two variables. So it's a numerical estimate of both the strength of the linear relationship and the direction of that relationship. So for example, the two variables might be two administrators of the same test. It could be ratings by two or more observers. It could be different forms of the same test, or it could be item comparisons within the test, like comparing one symptom with another symptom. Correlation really allows us then to predict outcomes. But while we talk about correlation, let me go off on a tangent briefly and point out that it's really important to remember that correlation is not causation. A really famous example of this concept, that correlation is not causation. And you've probably heard about this in one of your psychology classes. You may even heard this example in statistics in a basic statistics math class. But it's about the relationship between ice cream sales and murder. Murder. So this correlation versus causation example has been repeated multiple times in different areas because it is so easy to repeat. But in one particular instance, it was in 2009, the CDC reported that there was a national increase in homicide numbers between July and September in New York. The study was in New York, but they determined in that study that there was a national increase overall in homicide numbers between July and September. And then separately, a study found that national ice cream sales also increased between July and September. So the findings present a clear correlation between the two. When ice cream sales go up, so do homicides. And when homicides decreased, so did ice cream sales. But there's no evidence, of course, that ice cream sales cause murder or that murder contributes to people eating more ice cream. It might, but this study in particular doesn't prove that. It simply proves that the two correlate. And as we know, they also correlate with hotter weather. So this concept, that correlation does not indicate causation, it's a really important point to keep in mind because it highlights the flaws in using correlation as the sole determinant of relationship between two measures. So here's the example of a basic scatter diagram. A scatter diagram, you may also see or hear it referred to as a scatter plot. It's simply a graph in which the values of two variables are plotted along two axes. So you see that the x-axis is associated with the independent variable, and then the y-axis is our dependent variable. So you see that there's these dots, right? And they're kind of spread across this general area. And each dot that's showing there can represent a different score measure. And then by plugging all of those scores into the scatter plot, as you see here, you can determine whether any correlation between the scores is present. And this dashed line showing that the scores are kind of, in the most part, going up indicates that there is a correlation. In this case, it indicates that there might be a positive correlation that we're looking at. And you'll also notice that there might be a couple of, definitely at least one outlier. That blue dot that's towards it's remarkably below the other dots, would be considered an outlier. So it's also a means by which to identify whether there are certain points of measure that may be indicative of an error or for one reason or another aren't accurately representing what the other test results are representing. So the scatter diagram in general, it's this rectangular coordinate. You've got your two quantitative variables. And like I was saying, you've got your independent variable on the x-axis and the dependent variable on the y. It's not a frequency table. It's simply displaying the direction that these dots or measurements are going in. If the sign is positive, this means that the relation is direct. There's an increase in one variable and there's an increase in the other, or there's a decrease in one variable and that's associated with a decrease in the other variable. Those are situations in which we're looking at a positive correlation. So in other words, when the scores collectively go up or down together, it suggests a positive correlation. So before I proceed, take a moment to think of an example of a positive correlation in the counseling field about how something positively correlated with anxiety. Hopefully, you were able to think of one or two things that positively correlate with anxiety. The example I thought of first is anxiety and heart rate. So there's a positive correlation between the two, right? When the average person experiences increased anxiety, they experience a faster pulse. Another example is hours of sleep and energy. So when you get fewer hours of sleep, you have less energy. So in the first example, heart rate and anxiety, both rates went up. And in the second example of sleep and energy, both of the rates went down. And since in both of those examples, the measurements went in the same direction, we see that as a positive correlation. Negative correlations are when the scores go in opposite directions. So one increases while the other decreases. So now take a moment and think of an example of a negative correlation in the counseling field. Like maybe, let's say, how about something that's negatively correlated with depression? One really concrete example that came to mind for me would be the relationship between depression and socializing. So, as you know, isolating is a really common behavioral symptom observed in people who are struggling with depression. So, when the person's rate of depression increases, the frequency of socializing decreases. So we would see then that the two scores go in opposite directions and are therefore negatively correlated. Now, we can get even more specific about the correlation in terms of how strong or weak that correlation is. So the specific numerical measure of the correlation itself helps us to determine how strong or weak it is. If R equals 0, then there is no association or correlation between the two variables. Whereas if we're looking at R being less than 0.25, then it's considered a weak correlation. So there is a correlation there, but it isn't particularly strong. Whereas if R is kind of in between 0.25 and 0.75, that's more of an intermediate correlation. A strong correlation is going to be anything that's equal to or greater than 0.75 and less than 1. When R equals 1, we're looking at a perfect correlation. So test-retest reliability is the measure of reliability obtained by administering the same test twice or more over a period of time to a group of individuals. If you're retesting this just once, so we've administered the test twice, the scores from time 1 and time 2 can then be correlated in order to evaluate the test for stability over time. So it's a way to determine the extent of agreement that's measured between the correlations. Split half reliability, often referred to as internal consistency, is data collected that is then split randomly in half and compared to see if the results taken from each part of the measure are similar. This is another method of determining correlation and reliability. So for example, one half may be composed of even numbered questions, while the other half is composed of odd numbered questions. And then we're comparing the scores of the even to the scores of the odd and hoping that they both generally produce the same measure. And if that's the case, then we're seeing some internal consistency in this measure. So inter-rater reliability refers to the extent to which two or more individuals agree. For example, let's say that two people were sent to a hospital and instructed to observe the hospital's waiting times, the appearance of the waiting and examination rooms, and the general atmosphere of that hospital. Now, if both of the observers agreed perfectly on all of the items across this assessment or survey, then inter-rater reliability would be perfect. So ultimately, inter-rater reliability, we measure it by the correlation coefficient between the two ratings. And it involves having those two raters independently observe and record specified behaviors, or in my example, specified observations. A matter of observing and recording specified behaviors we look at the term target behavior, which is the specific behavior the observer is looking to record. So for example, if maybe we're looking for incidents of a client engaging in self-stimming behaviors like rocking in class, and maybe we want to see whether those behaviors are occurring consistently in certain settings versus not, the target behavior that we're wanting to identify is that rocking. And the target behavior that we're then wanting to measure and hopefully decrease over time is, again, the rocking behavior. Alternate forms reliability, first off, is referred to by a couple of different names. When you hear equivalent forms reliability or parallel forms reliability, we're also talking about alternate forms reliability. So all three are the same thing. And alternate forms reliability is obtained by administering two equivalent tests to the same group of test takers. To reduce risk of changes in environment or energy level or other factors, it's really important that the time frame between giving those two tests be as short as possible. The items on each test are matched for difficulty, and the alternate forms reliability is then measured by correlation coefficient between scores on the alternate forms. So in other words, alternate forms reliability is a measure of reliability between two different forms of the same test. So two equivalent but different tests are administered, the scores are correlated, and then the reliability coefficient is calculated. A test would be deemed reliable if differences in one test's observed scores correlate with differences in the equivalent test's scores. Now, when you administer a test, the final score on that test is called the obtained score. Pretty straightforward. But the obtained score consists of two parts, which are the true score and the error score. The true score is the person's actual ability, while the error is the difference between the observed and the true scores. Okay, so an example, let's say a student knew 90 out of 100 questions on a test. And then on the remaining 10 questions, the student guessed correctly on 7. And then they guessed incorrectly on 3 of the questions. So again, this is a 100 question test. The student 100% knew 90 of those questions. And then they guessed on 10 of the questions. Of those 10 questions that they guessed on, they were right with 7, and they were incorrect on 3 of their guesses. So in this scenario, the student's true score is 90 because that's the number of answers that the student actually knew. So yeah, they guessed correctly on 7, but they didn't actually know those. It was kind of luck or just much less reliable to determine whether or not they knew that information. So the student's true score is 90. That's the number of answers that the student actually knew. Their error score is the number of correct guesses minus the number of incorrect guesses. So in this case, 7 were the correct guesses and 3 were the incorrect guesses. So 7 minus 3 equals 4. And so in this example, the true score is 90 and the error score is 4. The standard error of measurement is a measurement of how much measured test scores are spread around a true score. So what does that actually mean? It means that the standard error of measurement is used to determine the effect of measurement error on individual results in a test. The standard error of measurement is a function of both the standard deviation of observed scores and the reliability of a test. When the test is perfectly reliable, the standard error of measurement equals 0. When the test is completely unreliable, the standard error of measurement is at its maximum, which, by the way, is equal to the standard deviation of the observed scores. The standard error of measurement serves in a complementary role to the reliability coefficient. Remember, reliability is the degree to which a test is consistent, repeatable, dependable. The reliability coefficient ranges from 0 to 1. So when a test is perfectly reliable, all observed score variance is caused by true score variance. Whereas when a test is completely unreliable, all observed score variance is a result of error. Although the reliability coefficient gives us information about the amount of error in a test measured in a group or a population, it doesn't inform us on the error that is present in that individual test score. And so that's where the standard error of measurement comes in. The reliability coefficient is a numerical representation between 0.0 and 1.0, representing the accuracy of a test or the accuracy of the instrument or rating. So remember, it's the way of confirming how accurate the test or measure is by giving it to the same subject more than once, and then determining if there's a correlation, which is the strength of the relationship and similarity between the two scores. A reliability coefficient essentially measures the consistency of scoring. When it comes to evaluating that measure, we have to refer to the test manual. So test manuals or other reviews of tests provide us with information on the test's reliability. Test developers, generally, psych researchers that develop these tests, they have the responsibility of reporting the reliability estimates that are relevant for a particular test. So the manual you can reference to determine what is the history of this test, what studies were done to validify this test, and so on. So when evaluating the reliability coefficients of a test, it's important to review the explanations that are provided in the manual. One of the explanations in the manual that we want to know are the types of reliability used. So the manual should indicate why a certain type of reliability coefficient was reported, and it should also discuss sources of random measurement error that are relevant for the test. The manual should also indicate how reliable studies were conducted. So the manual should indicate the conditions under which the data were obtained, such as the length of time that passed between the administrations of a test and a test-retest reliability study or something like that. Because in general, reliabilities tend to drop as the time between test administrations increase. We also want to know from the manual the characteristics of the sample group. The manual should indicate the important characteristics of the group used in gathering the reliability information. And that may be education level, occupation, age, gender. This will allow you to compare the characteristics of the people you want to test with the same group of people or the same type of group. If they're sufficiently similar, then the reported reliability estimates will probably hold true for your population as well. There are a lot of factors, of course, that affect the reliability of a test. When it comes to test length, generally the longer a test it is, the more reliable it is because it's giving more opportunities for information and data to be acquired and then measure what we're hoping to measure. The test-retest interval, or how much time passed between test 1 and test 2, is also a factor. The shorter the time interval between the two administrations of the test, the less likely that changes will occur. When there is little variability among test scores, the reliability will be low. And reliability will be low if a test is so easy that every test taker gets all the answers correct. And reliability will also be low if a test is so difficult that every test taker gets all the items wrong. So variability among the test scores matters. Guessing, of course, is going to be a factor that affects reliability. So if the test taker doesn't know the answer to any of these things and they're just guessing, that can be a fairly random process and isn't going to produce reliable results. And then variation within the test situation, like errors in the testing situation might be misunderstanding the directions, the noise level, other environmental distractions. These can cause the test scores to really vary across participants. Now, last week we talked quite a bit about validity. As a reminder, validity is the extent to which an instrument is measuring what it is supposed to measure. So if we're administering a test to determine a person's IQ, is this test that we're using effectively providing us with that information? If we knew for a fact what this person's IQ was, and then we administered this new IQ test, would that new IQ test effectively tell us the correct IQ of this person? If so, then we can consider that test to be valid. Criterion-related validity is a method for assessing the validity of a test, comparing its scores with another criterion that is already known to be a measure of the same trait or skill. It's measured by the correlation coefficient, which is, as we know, also known as the validity coefficient. So it's measured by the correlation or validity coefficient between the two scores. Criterion-related validity is most often expressed as a correlation between the test and the criterion measure. Okay, so for example, let's say the students are given this IQ test, and the teacher wants to know if the test will somehow predict the student's actual performance in this class. If the IQ test does end up predicting classroom performance, then it has criterion validity. Maybe another better example would be like a job performance test. Let's say a person in human resources is hiring for a new job, and as part of the hiring process, they give the applicant a test to predict how well they will perform in that job. Let's say then they hire the person that applied, and if that applicant's test score ends up correlating highly with their actual job performance later on, then the job performance had criterion validity. The job performance test did. Concurrent validity is a type of criterion-related validity, and it assesses the correlation between a new measure and an established measure that is taken at the same time. We can then use this to determine whether a new test can provide us with an immediate estimate of a person's ability or characteristic as it is measured by the test. So for example, let's say we're trying out a brand new mental health screening tool. So we give the test takers this brand new screening tool, as well as a more well-established psychological assessment at the same time. So these test takers are taking both back to back. First, they're taking this new screening tool, and then they're going to take this more established psychological assessment. If the results on the new screening correlate closely with the results of the psychological assessment, we can say that the screening that we're testing out has concurrent validity. Predictive validity looks at the capability of a test to foretell future occurrences or results. So this is a type of criterion validity that is specifically looking at future outcomes. If a test demonstrates a strong correlation between its results and future happenings, it has high predictive validity. So in that previous example about the job abilities test, if the pre-employment test is accurately predicting the applicant's future job performance, that pre-employment test has predictive validity. Content validity is the degree to which a test evaluates all aspects of the topic or construct or behavior that it's designed to measure. We want to know, do the items fully cover this subject? High content validity indicates that the test fully covers the topic for the target audience. Lower results suggest that the test does not contain relevant facets of the subject matter. Researchers, we find, often consider content validity when developing a psych scale, such as a depression scale for screening. Does the instrument cover the full range of dimensions related to the psychological construct, or does the instrument only cover a portion of it? Validity is the degree to which a test accurately assesses the construct that it intends to measure. So it involves evaluating the relationship between the test and the other measures or constructs to determine if they align as expected. So for example, in last week's assignment, some of you wrote about the PHQ-9 as a screening tool that can be used to detect depression. This is a really standardized tool that's used at a lot of programs. Let's say that you proceed to develop your own screening tool for depression. If we found that there was a high degree of correlation between the PHQ-9 and your new screening, there is strong construct validity there. An example of something with low construct validity would be if we compared the PHQ-9 to the GAD-7 with the goal of identifying depression. We know that the GAD-7 effectively detects anxiety, but it does not effectively measure depression. So in terms of measuring depression, the GAD-7 lacks construct validity. That affect the validity of a measurement tool are test-related factors, like the length of the test, ambiguity in the test's instructions, or maybe even an identifiable pattern of answers that makes it easy for the test taker to then guess correctly. Another factor is if the criterion to which you are comparing your test is not well enough established. So going back to this new depression screening tool that you decided to create, if we compare it to the PHQ-9, that's really a smart decision because the PHQ-9 is a really well-established test. However, if you compared your new screening tool to another new or lesser known screening tool, you still won't really know whether your test is all that valid because you don't really know if the one you're comparing it to is all that valid. Intervening events, including a big interruption in the test, or maybe the test taker becomes ill when it's time to retake the test, and so on, these are again factors that can affect validity. And of course, reliability affects validity. A reliable measure isn't always valid, but a valid measurement is generally reliable. So even if the results on your new depression screening are reproducible, they aren't necessarily correct or accurate. You could be giving the same screening over and over again and get the same consistent kinds of answers, but it doesn't mean that they're accurately reporting on this person's depression. A valid measurement, though, is usually reliable. So if we know that the PHQ-9 produces accurate results about a person's depression, then we should trust that those results will be reproducible.